Starship will never have landing legs. For years, that wasn't just a prediction, it was treated as fact. But now, SpaceX has officially confirmed the exact opposite. Starship is getting landing legs. And the reason behind that decision reveals a lot about where the program is heading next. Let's take a closer look. On April 21st, 2026, a Falcon 9 booster touched down on the Droneship. Just read the instructions for the 156th time, and for the last time in history. Almost immediately, SpaceX announced that the vessel would be reassigned to the Starship program, and that sparked a question across the entire space community. Is this the first step toward preparing drone ships for Starship landings? After all, Starship has gone through numerous flight tests without a single landing leg in sight. So, why would a drone ship matter at all? Unless SpaceX is planning to change that. But the answer is becoming increasingly clear. Starship is going to need legs. And when you look at the bigger picture, you start to realize this is no longer an optional design choice. It's inevitable. After Starship Flight 12, monitoring stations recorded some eye-opening numbers. The closest station, on South Padre Island about 6 miles away, measured sound levels as high as 125 decibels, roughly equivalent to a gunshot at close range. Even in Brownsville, 22 miles from the launch site, sensors still registered around 117 decibels, and that's from just a single test flight. Now, multiply that by SpaceX's long-term vision. Thousands of Starship flights per year, millions of tons of payload to orbit. At that scale, the cumulative acoustic impact becomes impossible to ignore. In May 2026, roughly 80 South Texas households filed a lawsuit against SpaceX, alleging that Starship test flights had generated shockwaves powerful enough to crack walls, shatter windows, and damage homes miles away. The plaintiffs presented physical evidence of property damage. So if SpaceX wants to reduce those legal risks while minimizing community impact, the answer is obvious. Move the landings out into the open ocean, where there are no windows to break and no homeowners waiting to sue. That's one reason landing legs make increasing sense. But honestly, that's still not the strongest argument. Here's the second one. Every time Mechazilla catches a returning super heavy booster, those steel arms absorb the full load of a 275-ton vehicle, slowing from tens of meters per second to nearly zero in under a second. Those aren't static loads, they're dynamic shock loads, the exact kind that accelerates material fatigue faster than almost anything else in mechanical engineering. Every joint, every rail segment, every hydraulic cylinder accumulates fatigue damage with each catch. Eventually, those components must be inspected, serviced, and replaced. There is no way around that. It's simply physics. The aviation industry learned this decades ago. Every critical component has a certified fatigue life. Once that limit is reached, replacement is mandatory, regardless of how healthy the part looks from the outside. If SpaceX launches 100, 200, or 500 times per year, Mechazilla will need scheduled maintenance. There will be days, potentially weeks, when the tower is offline. And whenever that happens, every vehicle scheduled to return during that window has nowhere to land. The only alternative would be ocean splashdowns. But Dragon was designed for that from day one. Starship wasn't. A vehicle covered in thousands of heat shield tiles, packed with avionics and complex aft systems, cannot be dropped into salt water and reflown a few days later. Once seawater gets inside, refurbishment becomes a massive undertaking. In some cases, beyond economical repair. That's the kind of cost and downtime SpaceX cannot afford at airline-like flight rates. At this point, the picture is clear. Starship is getting landing legs. And that raises the next question, because not all landing legs are created equal. The legs Starship needs for a drone ship are not the same as the legs it needs for a land-based pad, and neither of those look anything like what it will eventually need for the Moon or Mars. 3 vehicles, 3 surfaces, 3 completely different engineering problems, and of the 3, drone ship landings are in a league of their own, not because of salt water, not because of humidity, but because the landing platform itself is moving. A barge anchored in the open ocean is never truly stationary. It rolls with waves and oscillates continuously, often on cycles lasting just a few seconds. During the final moments of a landing burn, 3 Raptor engines are blasting tremendous thrust directly toward the deck below. And that exhaust interacts with both the water surface and the vessel itself, creating forces no mathematical model can predict with perfect accuracy. The result? Even if the booster arrives exactly where the guidance system intended, all 6 landing legs may not touch the deck simultaneously. One leg could make contact a tenth or 2/10 of a second before the others. And during that brief instant, if the barge happens to be tilted by just 2 or 3 degrees, a significant portion of the entire load from a 275-ton dry mass booster may be concentrated on only 1 or 2 legs. That's the kind of asymmetric loading that can lead to structural deformation or immediate stability issues right at touchdown. The most effective solution is active damping. Each landing leg would likely require its own hydraulic or electromechanical actuator capable of adjusting stiffness and extension length in real time using inputs from accelerometers and gyroscopes. Those adjustments would need to happen within mere milliseconds before touchdown is complete. That's an entirely different philosophy from Falcon 9. Falcon 9's legs are essentially passive systems. They deploy using pressurized gas and rely on aluminum honeycomb crush cores to absorb impact energy once and only once. Falcon 9's legs are a punch. Starship's Droneship legs need to be an open hand, constantly adapting to changing conditions moment by moment. And now, we arrive at the most difficult part of the entire problem, the one that receives surprisingly little attention: Super Heavy itself. Block 3. Super Heavy stands approximately 72.3 meters tall, with a 9-meter diameter and an estimated dry mass of around 275 tons. Its aspect ratio, height divided by diameter, is roughly 8:1. To put that into perspective, imagine a 20-story building balanced on a footprint only slightly wider than a living room. The stability principle is simple. The vehicle's center of gravity must remain inside the footprint created by its landing legs. After landing propellant has been consumed, Super Heavy's center of gravity is expected to sit somewhere around the middle of the vehicle, roughly 35 to 40 meters above the deck. With the center of gravity the high, even modest side loads from wind, barge motion, or touchdown imbalance generate enormous torque around the contact points. To resist that torque and prevent the booster from tipping over, the landing legs need to create an exceptionally wide footprint. Reasonable estimates suggest a radius of at least 20 to 25 meters from the vehicle centerline to the outer edge of the support polygon. That means each leg, when fully deployed, could be 15 to 18 meters long. That's nearly the length of a full-size railroad car. As for the number of legs, 6 makes far more sense than Falcon 9's 4. Not because 6 legs are inherently stronger, but because 6 contact points create a much more stable hexagonal footprint. Even more importantly, if one leg experiences an anomaly or lands out of phase, the remaining 5 legs can still form a support polygon large enough to keep the vehicle upright. With 4 legs, losing one is already a serious problem. Losing a second is game over. Material selection presents another challenge. Steel, which works well for Starship's primary structure, is simply too heavy for large deployable landing legs. The main structural framework would likely rely heavily on carbon fiber composites to minimize mass, aluminum honeycomb structures within the footpads to absorb touchdown energy, and titanium or high-temperature alloy steel near the engine section, where thermal loads are greatest. Altogether, a 6-leg system for Super Heavy could easily add 15 to 25 tons of dry mass. That's a significant penalty. But it's also the price SpaceX may have to pay for the ability to land virtually anywhere beyond Starbase. The upper stage Starship faces a completely different challenge. At roughly 50 meters tall and around 85 tons dry mass, it's both lighter and shorter than Super Heavy, making stability far less of a concern. But Starship must survive something the booster never experiences: orbital re-entry. During re-entry, temperatures across portions of the heat shield can reach roughly 1,400 to 1,600 degrees Celsius before the vehicle ever gets close to deploying its landing legs. Those legs would most likely be stowed inside the aft section, the very area exposed to some of the harshest thermal conditions during flight. Any deployment mechanism, whether hydraulic or electric, must function flawlessly after enduring extreme heating for tens of minutes. If a hinge jams because of differential thermal expansion, or if a deployment mechanism fails to actuate, you suddenly have an 85-ton spacecraft descending toward the surface with no way to support itself. That's why thermal isolation between the landing leg mechanisms and the vehicle's hot outer structure isn't simply desirable, it's mandatory. And that requirement adds a tremendous amount of complexity, engineering risk, and mass compared with any conventional landing leg design. So, the final question everyone wants answered: when will we actually see a Starship with landing legs? The honest answer is, not as soon as many people think, but not as far off as many people fear. Starship is currently on Generation 5-3, which made its debut in Flight 12 in May 2026. V3 is the version designed to carry out real missions, orbital refueling, Starlink deployment, and in the longer term, the groundwork for HLS. But V3 has no legs, not in the current design, not in any published technical documentation. V3 still relies entirely on Mechazilla for Earth return landings. Landing legs will arrive through two parallel development tracks, happening simultaneously, not sequentially. The first track is Starship HLS, the variant designed to land on the moon for NASA's Artemis program. This is the version that will have legs the soonest, because there is simply no other option. The moon has no Mechazilla, no flat concrete pad, and no one standing there to catch the vehicle. SpaceX is targeting an uncrewed HLS demo, landing on the lunar surface around mid-2027, ahead of Artemis actually putting humans on the moon under Artemis 4 in 2028. If that timeline holds, and that is a very large if, given that NASA's Aerospace Safety Advisory Panel has repeatedly warned that HLS is running significantly behind schedule, then 2027 would mark the first time we see a Starship variant with actual legs standing on a surface that isn't Earth. The second track is Earth landing with legs, including Droneship capability. This will come later, most likely alongside Generation VI4, the version SpaceX is targeting for a 2027 debut. V4 will stand roughly 20 meters taller than V3, will be considerably more capable, and based on everything SpaceX has signaled, it will be the first version designed for fully autonomous operation, meaning it can land anywhere without needing a tower. If EV4 debuts in late 2027, as anticipated, and early flights go smoothly, a Droneship landing attempt with legs could happen sometime around 2028. But SpaceX never commits to hard timelines for things that haven't been officially confirmed. And they've demonstrated more than once that Elon Musk's timelines are best understood as a direction, not a date.